Hello. Hi, my name is Fergal, and I'm the head of the perception team at Wayve. And I'm here today to share some of my learnings about working with perception and AI. So let me just set this up. Okay, so first of all, who are we? So we're a self-driving car company. Of course, this field is not new. They've been around for quite a while, and we have some very big competitors. Now, we believe that the reason we haven't seen self-driving solved is, one, it's of course very hard, maybe harder than we expected. And two, current approaches are being held back by their solutions. In particular, they're not adaptable or scalable. Initial approaches to self-driving have mostly been based around building up HD maps. This has taken us so far, but we feel it has a limit. They struggle to adapt to new domains and ever-changing locations like urban environments. Adding too many or building on top of very expensive or potentially unreliable sensors is also not a feasible solution to self-driving. So instead, we want to build the next generation of autonomous driving with end-to-end deep learning, something we've dubbed AV 2.0. So I wanted to give you a taste of what our system can do before taking a step back and looking at how we do it. And importantly for this talk, how we use data to achieve our goals. So this first scenario, showing us driving in complex urban scenarios in London with very complex intersections and ill-defined lanes and trajectories. In fact, it'd be very hard for us as humans to even define where the lane boundaries were here. The next one shows us driving in rain, something we see a lot of in the UK, and handling this obviously is different lighting conditions. We can also see driving down Oxford Street, the central business and shopping area of London. Well, shopping more than business, actually. But yeah, driving in down Oxford Street where it's very busy, lots of traffic islands and complex lanes, lots of buses, quite difficult to drive along, even as a human. Sorry. And final scenario, where we're in traffic, basically nudging and giving way, and it's quite complex and it's very hard to define rules for how to behave here. Obviously narrow gaps as well on the sides and motorcyclists and scooters pulling in and out in front of us. Additionally, stopping at a red light, something that we haven't told the system how to do. It just learns from expert data, sees that experts stop at red lights, therefore it should stop at red lights as well. So here's a taste of what we can do. And now on the topic of this talk, sources of data. So some exciting news we announced recently was that we've begun partnerships with Asda and Ocado. These are grocery delivery companies in the UK, allowing us to greatly increase our data collection and coverage. In particular, this device and camera fit, you can see on the left here, allows us to cover, we can fit it to vehicles and vans that are going out for doing normal grocery deliveries. And it allows us to cover 94% of the UK roads in a year, or in a month, actually, sorry. So a huge increase in data collection with these devices. So this is really exciting. So this enormous amount of data, it supplements our curriculum super well. In particular, we have other sources too. We have synthetic data from simulation and generative modeling, off-policy data, not only from our own fleets, but now delivery vans. And of course, hundreds of hours of on-policy data, where we measure performance and disengagements of our model on the roads of London. All of this data we feed into our fleet learning loop, enabling us to build a driving system which is general enough to work with delivery, ride-hailing across multiple cities and multiple vehicles. And we'll show more about these multiple cities later as well. Cool, so what do we do with our data? Thinking about the problem, our inputs are super high dimensional. We've got 6 monocular cameras running at 25 Hertz, and our output is a very low dimensional motion plan, as well as vehicle controls such as indicators and whatnot. So we are learning to drive with an end-to-end deep learning system, taking our input directly and predicting the motion plan. We can also have intermediate perception outputs to introduce structural biases to the network. These aren't perception bottlenecks, i.e. not a strict perceive, predict, and plan system. but they're more of like an intermediate representation or an auxiliary task. So a quick note about how to tackle your problem, as this really affects your data strategy. I'm not trying to advocate one or the other here, but some thought should certainly be given onto these two approaches. We've got one is a modular design and the other is an end-to-end system. Modular designs, such as those in like a typical perceive, predict, and plan to self-driving are really nice. They have all these great pluses, that particularly around with good engineering, you can test each component individually and get good metrics. But they have a downside. I mean, defining the interfaces is very hard. You've got to make sure that every bit of information from one module that you might need for the downstream tasks can get passed through. And so this means that if you're collecting data to label and do a task, you have to have a very long list of edge cases. For example, if you are trying to detect cars on the road as cuboids and you need that to drive, you start to think about, well, how do I know if a car in front of me is giving way or waving or is indicating or has hazard lights on? This list can grow very, very quickly if you have a bottleneck here. Of course, lots of edge cases to cover for each component with modular design, and further these intermediate metrics on like in your perception stack, say, detecting objects, might not be that useful for driving, particularly if an object is very far away or not in your driving path. These kind of metrics are maybe a little bit not quite custom to the end task. And the final thing is that errors propagate a lot with these modular designs. On the other hand, with the end-to-end style approach, the data strategy is a little bit simpler. It's just you've got to collect a lot of it. So having partnerships or data waterfalls of yourself is a solution here. You can have soft interfaces in the form of network features. So like we saw in the previous slides, we don't have a bottleneck here, but we have a soft interface. And so this ensures there's minimum information loss. You can always kind of have everything you need in the network without bottlenecking it. All the data is useful for all the tasks. Grading can flow from one task to another. So your control task can inform your perception, which is ultimately the goal. We want to know how to see what is only necessary for driving. But it does have some downsides. In particular, training can be slow. If training jointly, testing is very hard. You've got to cover all test cases for each new model. Errors can still propagate, but in a less understandable way. So yeah, these two approaches are tricky, and they will inform your strategy a lot. So coming back to the model, at Wayve, we've gone for the end-to-end approach, where we jointly learn signals like motion and perception, and we're going heavy on the data side, particularly of this input and these outputs. So what data do we need? For this training paradigm, I've kind of classified the data into two categories. Raw data, such as cameras, locations, motion plan, odometry, indicators, etc. These are the bare minimum for driving, and we can actually drive from these alone. You can go straight from an RGB input to a control output. On the other hand, we have perception data, and this is the area that I work with mostly, and as it commonly lends to, it's very good as it commonly lends lots of interpretability to the model, as well as enforcing some priors on what data is important. But importantly, you can't collect it with the sensor. You can't just put a segmentation camera on the car. Depth, you can kind of have LiDAR, but that has its own problems as well. So this is like, I guess, the cheap set of data, and the perception data is much more expensive. So how to handle these two sources is very important. So data annotation is very expensive, but it's sometimes unavoidable. The first question we've got to answer is, do we need labeled data? For the end-to-end approach, it's quite nice. You don't always need a lot of labeled data. And so this is something that's very useful for that. Additionally, sometimes it's possible to get data from other sources. For example, self-supervised depth using geometric consistency and structure for motion. I've kind of showed on the right a nice picture from a paper that I've referenced recently. You can actually get good depth estimation just from making sure that your depth prediction has consistency across time. And if you project features out into the world and back again for the car that's moved say a meter down the road, static objects shouldn't have like changed color or shape or anything like that. So this geometric prior for learning signal is very, very useful. We can also make fully self-supervised driving models, as I said, going straight from RGB to driving commands. And here I've shown a picture of what our depth can do without any learning or without any labeled depth data. So if you don't need labels, that's great. Try and use as much information as possible. But not all the time is it possible to use self-supervision. Sometimes we do need to pay for data. In particular, Wayve, some of the stuff we've collected has been semantic segmentation and cuboids, traffic lights, sign annotation, and some drivable area and lane line annotation. Note that we do have some LiDAR here. We want a low-cost sensor stack, but we don't necessarily need a low-cost data collection stack. So there's always a thing if a sensor can be used to solve some problems, it's great. Install it in your data collection stage, but maybe not in your model deployment stage. Cool. So this is the data we have. What can we do with it? I wanted to talk briefly about some of the work we've done recently on data enrichment and what it's allowed us to do. So, oops, oh no, my slide. These are supposed to animate a bit better than this. Ignore this 1 and 2 on the right. We'll come back to that later. So if we've just got this corpus of data in the center, as I said, taking RGB out in the roads and collecting all this odometry and video, we get a small labeled data pool, as I said, like segmentation and cuboids and everything, and train a supervised model. We add to that the self-supervision from depth and also from driving. You can train a model on your data, get the outputs and find out, what's hard for a model, and then save that back into your corpus. And basically enrich your data. So taking these supervised and self-supervised models, we can update what we've got. And now we've got 3 disks and their color rather than black and white. So we've got basically data corpus plus. And so this is super useful as it allows us to do 1, get better curricula animated, 2, get better metrics on our driving, and 3, allows us to do much better data cleaning. So the rest of the talk, I kind of wanted to talk, I want to spend some time talking about what this data corpus plus has allowed us to do, and these 3 topics, basically, the curricula, metrics, and data cleaning. As a final note, we can use these 3 tasks to kind of feed back into the labeled data pool. Something I'm not going to talk about too much today. I'm sure other people in this workshop will be talking a lot about it. Active learning loops and things like this, basically. So, curriculum generation. Not all data are created equal. Now, hopefully these videos will play. On the left, we've got randomly sampled snippets of driving data. Now, some of them are interesting, like pulling in there a second ago, but most of them are basically driving at the same speed and at the same steering angle. Okay, there are some mixed in. Maybe about 70 to 80% of data is I'd say boring, and maybe 20 to 30% is interesting. This is in London as well, so it's quite slow speed. So I think that number will be higher on highways, for example. You'd have 95 to 99% of data is uninteresting. On the other hand, if you change your sampling strategy to be looking for where speed or curvature of your steering wheel change, you can get much richer data, much more interesting. And this data is naturally much more useful for driving. So how do we get it, and how can we use it for our curriculum? So I'll let it play. See some more examples we've got. Slowing down, heading into roundabouts, turning sharp angles, very narrow streets. Going down, sometimes in London we have really narrow bollards and going through them, stopping, giving way, seeing something was blocked. These are all very interesting examples. So on to the next slide. Okay. So that's important, that not all data is equal. So here's a case study that we did recently in the perception team. So improving pedestrian safety. We were noticing high intervention rates around pedestrian crossings. So we decided to do some R&D experiments to inform how we can handle this basically in the product. So this is quite nice as it kind of fits nicely into the topic of the day. We had two approaches to this. We had two people saying, no, I think this is the way to solve it. The first one was a model-based approach. So let's say, look, we were handling pedestrians not too well. Let's solve this with model enhancement. We can add an explicit pedestrian detection model. Feed this into our controller, and the neural network should learn what to do. And so here's an example of what we're looking at. A bird's eye view grid on the bottom right, showing that we can detect pedestrians nicely, the depth of them, and even their orientation, their heading. So we said, okay, well, let's add this into the model. The other approach was to solve it with data. Let's do a curriculum change. As we saw earlier, not all data is equal. We're not handling this one area too well. Let's upweight that section. So we went back to our data corpus. We looked at all the semantic segmentation that we'd filled into our data. And we said, okay, well, let's query for zebra crossings. Crosswalks, you might call them as well in other countries, I'm not sure. So we upweighted those data, and we also had our on-policy data, and we looked for corrective actions around pedestrian crossings. So, okay, let's also upweight this. So in simulation, our baseline model violates the safety rules. It sees a pedestrian and it wants to avoid it, but it should be stopping, letting for the pedestrian to clear from the crossing before it goes ahead. So this is what we started with in our baseline, or our reference, should I say. First iteration of changing the curricula was okay, but we started to stop at pedestrian crossings and not continue onwards. So we said, okay, well, actually, maybe our curriculum isn't the best. We may be upweighting too much on the stopping scenario, so we can add some more going away. And with a little bit more tweaking, we get a much better model that now slows down for pedestrians and waits for them to cross before going on. So we test this in sim. Obviously, this is a R&D effort. So before we go out in the real world, and we see success as well in the real world in our tests. So the learning here was that the model approach was very tricky to get right. In fact, we were still kind of playing around with the integration methods and architectures. How should we get this top-down bird's eye view perception of pedestrians and feed it in? What should our weights be, our architecture? A lot of decisions to be done there, even though it seems like an easier solution. Whereas the data was just a couple of iterations, change it, and basically it worked very well. Now, of course, this is a little bit simple of an example. Generalizing data curricula with all of these hard examples is very tricky. Hard example mining is a super interesting topic that we're going hard on as well. But it was very satisfying to reach a conclusion so quickly without lengthy engineering and research into model development and architecture iteration and search and everything. So this was a super nice way of doing it. Okay, the second point, metrics. Metrics are super important for self-driving. So talking about something like kilometers per intervention is not that useful. We saw earlier that all driving kilometers are created equal. Sorry, that's wrong. They're not created equal. If you're getting hundreds of kilometers per intervention on a highway, that's very different to getting hundreds of kilometers intervention in central London or central Paris or Berlin. It's much, much harder in urban environments. So instead, we've been focusing on building metrics that make that are generic and scalable and are more about driving scenarios. So what is this? Some of these scenarios are easily categorized. I have them on the right here. Text is a bit small, but you've got things like turn left, following lanes, turning right. That's very easily got from odometry and maps. But other involve a little bit more information, which is where perception came into it. Things like stop at a traffic light, or did it run a red light? Did it stop at a green light? Does it do well in presence of pedestrians, cyclists? All these extra metrics. So these are very, very helpful for kind of building up, and useful to go to the corpus to get that. So recently, we did a generalization experiment, and this we announced on our blog a couple of days ago. I'll just play this video. It's only a minute, hopefully it's not too bad. I'll keep the audio off. But basically what it was is taking models that were trained on data in London and seeing how well they generalized to different UK cities. Is it possible? First one is Cambridge. This is where Wayve started, so it's a natural home for us. We go to Cambridge, very nicely handle it. Coventry, a bit further away. Going to Leeds. Manchester. And even Liverpool. There's some fun music as well. If you do want to check out the YouTube, I do recommend looking at the blog. So yeah, okay. What was my point about metrics here? So this is the blog link, by the way. It was really important to know that we were generalizing, basically. As you can see from these charts, we've selected cities and routes that varied a lot in terms of road layout, road features, driving complexity, traffic density, and so on, basically. For example, in Manchester, there's more pedestrians and bus lanes and traffic lights, whereas Leeds has almost 4 times as many cycle lanes. Great to see. And Cambridge is also, where's Cambridge? Cambridge is in light blue. Lots of cyclists in Cambridge. Yeah, naturally. So this kind of analysis based on scenarios and breaking down into events and atomic tests has been super useful for confirming for us that we can adapt and generalize to new domains. So again, this all came from and stemmed from this data corpus plus and this enhancement that we did. So on to the next slide. Final thing I wanted to talk about was data cleaning. So here's a rough overview of the progress at Wayve. So you have to excuse my hand-drawn graph. Y-axis here is some measure of driving performance, whether that be some course metric like kilometers per intervention or success in scenarios. So the general trend is a slow and steady march upwards with occasional jumps in performance. These jumps are quite interesting and usually the result of a long-term focused effort. A recent such example of this was when we moved from perspective space representations to going to bird's eye view. And there was a bit of work we did on our blog, you can see, about predicting in bird's eye view. But the other interesting part of this graph is these slow, steady marches upwards. And now these usually come from relatively straightforward data cleaning efforts. They're always super important. And in a big corpus of data, it's surprising how often you can find data that should be removed, or at least should be held aside until a later date, e.g. if it's too hard for the moment and you want to come back to it later, or if it's out of the driving domain. Just for fun, in the last few minutes, I wanted to go through some of these recent examples of unclean data that we found and how we found them. So this first example shows something that's the dirge of anyone working with multi-sensor systems, which is synchronization issues. Let's see if I can play. What do we see here? So we were plotting the odometry on top of the video, and you'll notice that as the car turns the corner, the path in red is still to the left, and then it catches back up later. So what does this mean, and how has this happened? What it means is that the video stream has gotten out of sync with the odometry we've measured. So this is really bad for training, as now we're telling our model to go to the left, basically, on this straight stretch of road. So it's super important to get rid of. Fortunately, once you find it, it's very easy to then write a rule to get rid of it. What happened here was basically that 2 clocks got out of sync, and then our system that merges them could no longer figure out which one was which. And so it had time slippages, basically. But very easy to remove. Okay, next one. Go to our data corpus, look at our images and say, hey, show me all the examples where the grayscale is below threshold. Night driving is very hard, but it's really hard when your exposure is incorrect. And so a simple check allowed us to find this underexposed data, which was corrupting our data sets. And it was straightforward to kind of put this aside until later. And finally, it happens in London a lot. Sorry, this video isn't the highest quality. I might just change the playback speed to be 0.25. But it rains a lot, as I mentioned, and sometimes you can get rain on your sensor, which isn't great. So here I've got the query is number of pixels that are of this class. Visual obstruction is greater than a threshold. Of course, we need a hardware solution to this, like a hydrophobic lens. But going back to your raw data and trying to remove and find this is really, really hard. But with this data updating effort, it was quite simple for us to do. Cool. So summary of all this is that money and time spent on understanding your data corpus pays off a lot. Annotate some of your data with an expert and the rest with a model. Making a queryable data engine speeds up model development a huge amount. Leveraging annotations to build test metrics speeds up time to results and understanding, and is very useful for confirming. And finally, data cleaning is very, very important. So yeah, that's all I wanted to say. And if you share our vision, please get in touch. We're hiring and we'd love to see you on board. So yeah, thank you very much.